Everybody. Just thought I'd give you a brief rundown of the serial program peripheral interface for the Arduino. It's a 3-wire full duplex synchronous serial transfer interface. Full duplex means 2 ways. You have an output and an input from your master, that would be your Arduino, to the slave, that could be your sensor, your output device, whatever you like. It's synchronous, therefore there's a serial clock involved, and you can select multiple output devices or input devices using the serial select. This is slave select. If you look at it in a different way, it's really just a shift register, shifting bits out synchronously in accordance with a serial clock to a slave, which has a shift register and shifts the bits in accordance with the serial clock. And the output from the slave goes to the input of the master, and the output of the master goes to the input of the slave. A MOSI, master out, slave in. MISO, master in, slave out. You can chain these things together with a slave select bus and select which slave is active. When a slave is not active, then you can proceed to, well, how would you put it? Run the slave into a high impedance state so it doesn't assert the lines. This is a daisy chained configuration where the master in and slave out are daisy chained from the various slaves with only one slave selected at a time. So here is a serial peripheral interface in the exploded diagram, and you can see there are several registers involved. There's an SPI control register, a status register. The control register changes how the finite state machine and the SPI interface works. There's a clock logic coming in from the SPI input. This is so-called synchronous, so it needs that clock, and it has to be generated externally. And here we go. Now we get to see the Arduino, and there's this little tiny header we haven't discussed, and it's called the in-circuit serial programmer header, the ICSP. And the ICSP header is all about SPI. This pin is the MISO. That pin there, pin 3, that's the serial clock. This pin, that's pin 5, that's your reset. This pin, that's pin 2. They're calling it VCC. Then comes pin 4. That's the MOSI, or master out, slave in. And then there's ground. Now, as it happens, these are wire-ORed with various pins on the side. And the question of which pin is which for various Arduino flavors is kind of open. In the Uno, pin 11 is assigned as the MOSI pin, and it is wire-ORed to this pin right here. That's pin 4. Then there's MISO that comes next, and that is wire-ORed to pin 1. That's that pin there. And you could measure actually the connectivity between pin 12 and pin 1 on the ICSP connector, and you'll see that they're connected. Here comes pin 13. This is the one we use for our little surface mount LED device. Now that's supposed to be the same thing as the serial clock, which would be pin 3, that pin right there. And here comes pin 10. That's supposed to be the serial select, and that serial select does not appear in the ICSP connector for some reason. And then that covers it. I don't quite understand why the serial select isn't here. Perhaps it's meant to be wired separately. So now that you've seen shift registers shifting the bits in and then shifting the bits out, the SPI clock gets distributed to the various shift registers. And what you can do is you can find a wide variety of different SPI interface chips that you can wire to. This is a de facto industry standard that was started probably in the early 80s by Motorola. I did a little historic look on this, and there's some debate about that. So slave select. If SPI interface has no control of the slave selected master mode, it can be a bit of a problem. You don't necessarily want to have it held high, or else you're going to end up being in slave mode. So here comes a serial peripheral interface control register, SPCR, and now we can see the individual bits which are used to control the SPI. Here's the interrupt enable. I would expect an interrupt to occur and to get serviced if a peripheral requested it, if there was data ready. SPI enable, that enables the SPI interface. Data order, we typically want the least significant bit to be first. Master slave select, if we select that, we can change from master mode to slave mode. Here is clock polarity, that's a phase shift. Here's clock phase, and we could choose whether we want leading 0 or to trigger on leading edge or the trailing edge. And then we've got 3 bits in through here. Or is it 2? Yeah, 3 bits. The first bit is the SPI2X, SPIR1, and SPIR0. And these bits allow us to change some oscillator multipliers, the speed, essentially, of the SPI interface. There's an SPI status register, and you can put in an interrupt flag, so when the serial transfer is complete, you get an interrupt. If there's write collisions, you can get an interrupt on that. You can choose what the clock rate is within limits. You can double the clock rate if you want to go faster for whatever reason. And let's see. We've got an SPI data register, and that's actually the shift register that's going to get shifted out. That goes right into the shift register, and you can read it or write it depending upon whether you're sending or receiving data. The 9-bit shift register, that's used for parity. And this is a TTL implementation of the SPI interface to an LCD display. So what we have here is our little shift register. We've got a couple of D flip-flops, and we've got a mechanism whereby we can take data, input it into the shift register, and then have it appear on our little LCD display. Over here, the 74164, you can see the pinout of the actual device. We might even have some of these in the lab somewhere. Here's some bit flippy code. The data direction register is being set over in here. Here's the control register for the SPI, and here's the status register. And this is all being done during the init phase. And now we're going to create we'll call it a multiplying DAC or digital pot that essentially we're going to write to and change its values of. And what's happening in here is it's probably sitting on one of the ports. This is port F, and that's going to enable us to do our write. So now we've got an example with the microchip MCP, a 42XXX DAC. This is the digital to analog converter that's built into your audio shields. And that enables you to take data, 10 bits worth of data, and output it to the DAC, and then have a digital to analog conversion experience, if you like. Here's a register with tri-state logic on output, and this tri-state element in here, you can see there's a negation twice, so it's going to just act as a simple tri-state buffer. And this is the 74HC595, which is a very good SPI peripheral. We can use this to act as a slave that takes serial data in and parallelizes it. So now, if you want to read from the SPI port, you can do that as well. Here we have the SPI data register, and here is another view of the 74HC165. HC stands for high-speed CMOS. That's available in DIP, that's dual inline package, SOIC, that's small outline integrated circuit, SOP, that's small outline package, and there's a package that's kind of like a quad flat pack T SSOP, another microelectronic device configuration. This is the box with transparency showing the Arduino shield mounted on top of an Arduino, and there's a stomp switch on the top. This is a stomp box that was sold on Kickstarter. And so what we'll do is we'll take a look at a Kickstarter project that has the shield in it and see what that looks like. So let's have a looky-loo at that. So what we'll do is we'll bring up the URL for that. This is called the Arduino Audio Shield, and I think we can run it at full screen and see how it looks.
Real-time effects that make audio processing fast and fun. The Shield enables you to create unique effects all your own.
I, for one, welcome our cyber overlords.
Just imagine how jealous your signal processing neighbors will be when they view your hand-built, custom virgin plexiglass cases available for the office or home in either classic clear or glamorous gold. Why buy one when you can buy two for stereo?
The optional laser cut case is held together with threaded metal feet for ruggedized field performance. An optional hand-built industrial strength die-cast aluminum alloy case is available with stomp switch.
Exterminate them.
The Arduino Audio Shield is designed to make signal processing easy, giving you amazing sound effects at a great price. The Shield can run on a 9-volt battery for portable deployment. To make this a reality, I need your support. Your contribution makes quantity production possible. Be the first to experience it yourself. Early backers will get limited quantity access to bundles that include free. That's right, you heard me. Free shields and cases. If you wait and miss out on this offer, the angels will weep for you. Buy multiple shields and hook them together to create new effects. Come up with unique sounds all your own. The Arduino audio shields are autonomous and can work independently, either on USB power, AC power, or battery power. Purchase multiple audio shields to combine sound effects. All audio effects are performed in real time. Once configured, no host computer is needed. Just add an external 9-volt DC power supply.
Our first 10 are just in from production, and here they are, hot off the soldering iron press. Get your audio shield today. And don't get stuck in a loop. Oops.
So I hope you liked my little demo and my little presentation on the Audio Shield, and we'll be learning how to program that a little bit later on. Thanks a bunch. Stay safe.